All right, kids, here we are on page 37, starting with resonance hybrids. A hybrid, keep in mind, just in everyday language, is a mix of two things. Like, you may know what a labradoodle is. Well, it's a dog mix between a Labrador and a poodle. Well, for resonance hybrids, it's actually a mix or a combination of different structures, okay? So that's what we're looking for here. So anyway, there's a rather large class of molecules for which one has no difficulty writing Lewis structures. In fact, we can write more than one valid structure for a given molecule. So this raises a new problem. How do we decide which one to use? The answer is simple. If the structures are all equivalent, we use them all. An example, consider the nitrate ion, NO3 -1, for which 3 Lewis structures can be written. Take a look at these examples here, or take a look at the pictures here. We have 1 nitrogen and 3 oxygen. Notice that here we have a double bond. Well, the only difference from the first 2 pictures is that the double bond is on the right side and then the double bond is on the left side. Everything else, though, is perfectly equal. Take a look at the last one. Again, the only thing that is changed about this structure is that the double bond has moved. So we have the double bond on the right, double bond on the left, and then double bond at the bottom. Other than that, though, it's the exact same structure. So when we get an overall picture of all of these, we look at it as a mixture of all 3 structures. Okay, so these structures differ only in which oxygen is attached by a double bond. Since there's no reason to prefer one over another, the nitrate ion is regarded as a superposition, meaning all 3 of them stacked on top of each other, or a hybrid of all 3 of these structures. The term resonance has been used to describe this phenomenon, which is indicated in the above structures by the double-ended arrows. So anytime we're going to do resonance structures, we're going to use brackets, right? Square brackets. We're also going to indicate resonance structures using our double-sided arrows. Okay, let's take a look at our 2 examples. For our first example on resonance hybrids, we have O3. I wonder if anybody knows what O3 is. Anybody? Anybody? Just kidding. No, I can't hear you. But anyway, O3 actually has the name ozone. You've probably heard of that before, right? You've heard of the ozone layer. Well, O3 is that molecule. Okay, so don't let it trick you. It literally means 3 oxygens all bonded to each other. So we're going to have O equals 3 times 6, since 16 is the group number of oxygen. And that's going to give us 18 electrons to play with. And again, don't overthink this. It's oxygen bonded to oxygen. And we're going to follow our same steps. So we've used 4 of the electrons, subtract that out, and that's going to leave us 14 to use as lone pairs. So we're going to take 2, 4, 6, 8, 10, 12, and 14. Okay, we've used up all of our electrons, but there's a problem with our central oxygen. The central oxygen, the way we've drawn it, only has 6 electrons surrounding it. So then whenever we run out of electrons and our central atom does not have an octet, remember that's when it's time to share more pairs. So I'm going to take the electron pair from one of the oxygens, and that's going to give me enough electrons around the central oxygen. Now, why did I choose this oxygen to take electrons from and not this oxygen? Or could I have done it the other way? The answer is yes. You could have taken it from either one. So then what we wind up with is a resonance structure. We could, at one given time, take electrons from the oxygen on the right, and that would end up with this structure. right? We take the lone pair that we circled, move that in to become a double bond, but all of the other electrons should stay the same. Well, that's one of the choices. The other choice is to take it from the other oxygen. Okay, we could have very easily moved it over from one. Now, at any given time, we only need to move one pair of electrons, and that's why we end up with these hybrids. So in this other structure, it's the exact same thing, except notice that the double bond is on the other side. And again, we want to be careful with how many lone pairs we put on each oxygen. The doubly bonded oxygen should only have 2 lone pairs, whereas the singly bonded oxygen should have 3 lone pairs. And overall, both of these structures overlapped on each other is what is the structure for O3. Okay, go ahead and try the next one on your own, and that next one is SO3. If you're having any problems with any of this, it's time to speak up. So during class, you need to make sure and ask questions. All right,